It's in this season of the year, right around the start, when we begin at the beginning of the semester and start teaching physics, that I'm talking a lot about fundamentally what physics is. I've been doing a lot. It's been my past couple days. I've been talking to people about what is this physics. And of course, that's a subject that I could go on and on and on about, talking about exactly what it is, what it means. There are books that are written on the subject, and so there are lots of different ways to come at it. But the fundamental thing that it comes down to is that physics, like all sciences, but in particular physics, the observational science, what we're doing in this course, in this classical physics course that we're going to do, is we're looking at the universe and observing the fact that there are rules. We live in a universe that's based on rules, and finding out those rules is really the game of doing physics. And naturally, we know that those rules express themselves as physical laws, a form of equations that I can write down and relationships that I can manipulate. But it all comes down to observation. And the fundamental nature of observation is something that we've discussed at length previously, some of us together, and that is measurement. Observations of our universe begin with making fundamental measurements. Now, there are some measurements that are truly fundamental and others that are not. And in particular, for our course, what matters is that there are two fundamental measurements of importance to us, and they are position and time. I measure the location of objects in the universe, and that necessitates that I choose a coordinate system in which I make those measurements. So I choose a coordinate system, and that just means choosing a place that is zero and choosing a direction that is positive so that I can mete out tick marks on some sort of scale, which by now we're all very familiar with. And I can locate a position of an object. And the symbol that I use for position, particularly when I first begin talking about mechanics, is imagining mechanics in a one-dimensional way, is x, the position of an object or an event in my universe. So I write x as the position. I try not to write too much in the way of words on the board because there's a little bit of silence when I'm writing. But x is the position, which is the location of an object or an event in the universe in some coordinate system. And that's really my first fundamental observation. My other fundamental observation is time. Now, just yesterday I had a wonderful, every once in a while you just say at the end, you get to the end of a long discussion, and you say to folks, does anybody have any questions? And a young man very bravely says, what is time? Which is a spectacular question, very deep, something you get into and discuss. Well, the answer to that, of course, is that there's a great deal about time that we do not understand fundamentally. Like, for example, why does time exist? Well, I don't know. It's a fundamental feature of the universe. When I say universe, part of what I mean in that very big word is the existence of time. But I have to give the young fellow a satisfying answer. So what I said was that time is defined in terms of its measurement, just like position. I choose a standard of measurement for position. I create a coordinate system. I mete out some meters along a coordinate axis, and I say, bang, position. That is a number associated with the idea of location of an object or event in my universe. Well, the same thing's true of time. I get a string and a mass, and I hang from it. I swing it back and forth, and it's a pendulum that has some regular motion. When it swings back and forth, I call that 1 unit of time. Perhaps I've been clever. And I build it in such a way so that it's exactly the right length so that it swings back and forth in a second. I call that 1 second of time. And now I can mete out intervals between this event and this other event that happens. Otherwise, that has no idea. If you think about it for a bit, it freaks you out. Now, and then now. Oh, and now, but then, and now, but now is different, and it just keeps on going. So it's a very abstract sort of thing. It's difficult to get your head around. Why is time moving forward? Why sometimes does time seem to move very rapidly, like when you're having fun, and time seem to go very slowly, like when you're sitting in a physics lecture? Why is it that our perception of time is that way? But when I build a pendulum and swing back and forth and call it a second, now I can assign a numerical quantity to that thing. You know, a thing I've been pondering recently, I don't want to get too philosophical because I have rather technical issues to get into, but a thing that I ponder very often and have discussions with students about is, why is the universe mathematical? You know, it's inherently mathematical. All physical laws that we've discovered that describe the natural behavior of our universe express themselves as mathematical equations. You say, well, Shadley, I'm not gonna go with that. I'm going to make a non-mathematical version of physics where I can draw conclusions about the nature of the behavior that I observe in my universe, but there's no math involved at all. Kind of physics for poets, right? It's just all words. It's been tried. For example, if you take a universal law like gravitation, you'll find, perhaps much to your chagrin, that the universal law of gravitation is expressed as a mathematical law. because there's an equation that governs the amount of force that I encounter between two massive objects separated by some distance in space. Little GMM over r squared, for those of you who recall and are familiar with that. So I can calculate the amount of force, and based on the force, I calculate the acceleration and the motion through space. Right? Now, I don't want to do that. I don't want that law to be mathematical, so I have a clever idea, you see. This is what I'll do. Imagine that the way that gravity works, this is a version of universal gravitation in words. We're going to try to make a non-mathematical law. That the reason why there's gravitation is that in the universe, there are these unseen, undetectable particles. You see, I'm already off the rail there because I've had to invent a fantasy in order to fill in for the parts of it that I don't deeply understand. But for the sake of the argument, the universe is filled with particles and they're going every which way. And so when I stand in the middle of the universe, these particles are hitting me in every direction. And so the net effect that they have on me is zero. Because for every particle that hits me going this way, another particle hits me going this way. And so the total influence of them is, on average, nothing. So there's no effect. So consider a situation where I have the sun in space, and it's being hit in all directions by all of these particles, and so the total effect is really nothing. But now, here's the Earth in proximity of the sun. Now a curious thing happens. The sun is blocking some of the particles that would come from this side. And those particles hit the sun and then don't hit the Earth. So over here on the Earth would be getting hit from all sides, but it's not now. Now there are fewer particles on this side and more particles on this side, so the Earth feels a net influence toward the sun and therefore curves away from its otherwise rectilinear motion by the influence of excess particles on one side. And it turns out that that idea in words, if you use it for observation, that the number of particles striking would diminish as 1 over the square of the distance, just like gravity does. Yay! There's a law of gravity that's not mathematical. The trouble is it doesn't work. Because then as the Earth proceeds along its orbit, the Earth would be hitting more particles in the direction of its travel than it would be leaving behind. And so it would encounter a kind of viscous drag force as it traveled through space, which is a thing we don't observe. Every opportunity that's every effort that's been made to create a universal law that is not mathematical has failed. So the question is this: why is physics mathematical? You know, lots of students would rather it wasn't, because it's the math that gets everybody. It's what people complain about. I've been saying, don't get mad at the physics, get mad at the math. It's not physics' fault. The nature of the universe is purely mathematical. And why? And I think I just said so. Because the fundamental observations that we make of the universe are ultimately quantifying an observation. The location of an object in the universe. I choose a coordinate system and now all of a sudden it becomes a number. Or I build a pendulum and I let it swing back and forth and all of a sudden it becomes a number. And as soon as it's a number, I'm going to add, subtract, multiply, and divide. I'm going to find relationships that are ratios or whatever, and the whole thing becomes suddenly mathematical. There's no way to make quantified observations of the universe and not have your physical laws ultimately express themselves mathematically. So here's the very start of it. Here's where all that trouble gets started. Here's where all the equations of physics come from. That I make the choice to quantify the location of an object or an event in my universe. Well, this is a very simple description of the universe. Then all I'm going to do is I'm going to locate the object of everything that is or ever was. Well, no, that's not true. I'm going to locate the location of everything that is in the universe, and I'll assign everything a position, and then I'll look at the universe and I go, there it is! Snapshot! I know the location of everything. I can tell you the number that represents in this coordinate system that I chose arbitrarily. I can tell you the number that is the position of everything in the universe. Great, I'm done. Now I can go fix the air conditioning. The trouble is, while I'm off fixing the air conditioning, I come back again, and everything's changed its position. It's the wonderful thing about the universe, that it's dynamic, that things in the universe change their positions. And so I look for the location of all of the objects in the universe, and I find they've all changed. All those numbers have changed. So that's a new phenomenon of the universe that I have to make a measurement of, or have a description of. Naturally, the description that we have of that is that we calculate the change in position. Now, a quantity that I write here, delta x, the change in position. Delta always means change in science. Delta capital T might be change in temperature. Delta Q might be change in internal energy, right? Delta quantities are the change in, later on, delta capital B, the change in magnetic field. Delta means the change in a quantity, and it's the very first equation of physics that we get, because it's equal to the final position, x, minus the initial position. That is a quantity that we call displacement. It's not the same thing as position. It's not the same thing as position. Sometimes it coincidentally is. If I call the initial position 0, then sure, the position and the displacement happen to be equal to each other, but that's just a coincidence. If I'm being very precise about what I say, Displacement is the change in position. Displacement is a quantity of interest because it describes for me the evolution of my universe. It describes for me the evolution of my universe, this change quantity, known as the displacement. I suppose I better write displacement here on my notes just for displacement. I will probably do some horrible misspellings as we go along. Feel free to interject as soon as you see me write something that's terribly wrong. But the change. But when I observe the change in my universe, something really interesting about it I find is that I observe one object in my universe and I find its position to be here in some coordinate system. And then when I come back again, I measure its position again. I find that it's 2 meters different from where it was before. And that's quite remarkable. It was here and now it's 2 meters away. I have a meter stick that I've used, a standard of measure, and it's 2 meters away. But then there's this other thing here that in that same time that I was gone, that I was not paying attention to the universe, it moved 5 meters in the same interval of time. Now time becomes an issue. I observe that the changes in position are not equal in equal intervals of human experience. And so in order to quantify that, I create the notion of measured time. Well, to measure time, I need some standard. My standard of that, of course, will be the second. And I'll measure out time in seconds, and now I have a new quantity that I define, which is the change in the position, that is the displacement, delta x, divided by the time in which that displacement happens. It's the rate of change of position. Now, my displacement, of course, has units of meters. This is a Scheidleism that you'll see some of you are familiar with. Whenever I'm describing the units of a quantity, I'll put it in square brackets like that. My displacement, I'm going to measure my standard unit as meters. As we go through and you do assignments and things or calculating things, there are going to be different units you'll have to convert throughout our SI unit system. But I think at this point you're very familiar with it. This quantity, the displacement divided by the time in which the displacement happens, this quantity would have units of meters, because the displacement is in meters, divided by seconds, our SI unit for time. And so this unit, or this quantity that I've invented here, has units of meters per second. Well, there's no suspense at all in the room about this. This quantity, of course, is the velocity. The velocity is the rate of change of position. So naturally, velocity with units of meters per second. So now I've got a much better version of my universe, in fact, that I can look around and I can look at the positions of all the objects. And I can turn my back for a second and look back again, and I can see all the new positions, which means I can calculate all the velocities. So now I understand my universe in a much more sophisticated way. Does this not mean that my classical mechanical description of physics that I'm going to now present over the course of however many weeks that we do this, doesn't that mean that it is an approximate description of the universe? Absolutely. Now, as a young student, you may hunger for the exact description of the universe. Well, I'm terribly sorry to disappoint you. We don't have one. We don't have one. And you'll find that this description of the universe, based on these ideas, is in itself fundamentally imperfect. Fundamentally imperfect. And we've discovered this only in the modern era of our physics. This is the really fun part of this. It's really remarkable. I know that some of you are looking at this and going, yes, position, velocity, acceleration. Come on, position, velocity is very, very obvious. Come on, nom. But there's something fantastically deep about this. So let me take this very, very simple physics and let me just for a minute, zhuzh it up a little bit. I had mentioned about units and fundamental quantities and said that the position, which I measure in meters, and time, which I measure in seconds, are like really fundamental quantities. The reason why I mentioned that is that when I create new physical quantities in my classical mechanics, when I create new physical quantities, they'll simply be combinations of space and time. For example, meters per second. Meters per second is less fundamental because it's got meters in it and it's got seconds in it. It's got meters in it, it's got seconds in it. Now, I don't have any use for it at the moment, but another fundamental quantity, again, that is defined only in the context of its measurement is mass. A certain number of grams. What does that mean, that a thing has mass? What does it mean? This is great, right? Just to think deeply about, just for fun, because it doesn't go anywhere. But here we are, and time is passing. Like, stop for a moment. Like, time? What, time? Right? No, sit really still, and then time won't pass. Well, you can't do that, can you? Can you sit completely still? No, because all of your molecules are vibrating and everything, and things are happening, respiration and whatnot. The universe is inherently dynamic. You cannot stop time. It proceeds. What is time? It's defined only in terms of its measurement. Jeff, think deeply about this. You're there, and I'm here. The hell is that? Like, space exists. That's a shame that you can't get that gesture on the recording. Space, what? But you're, pardon me, okay, let's just live with that. You're there and I'm here. A meter. Now it has meaning, right? A meter or two, not really, a meter and a half, or two, right? Now space has, that's the only meaning that it has in the context of its measurement. Well, an observation that we'll make is that objects in our universe have a tendency to persevere in their motions. That's the thing that I'm going to be talking about next week very, very intently. I'm going to spend an entire block talking about that. That objects persevere in their motions. It's their natural tendency to do that. Why, Shidley? We don't really know. As a matter of fact, it's kind of an exciting time in physics a little bit. Science proceeds slowly. And you can sort of wish for things to happen in your lifetime. I would wish for it to happen in my lifetime that we would understand fundamentally why mass exists. But only just recently have we begun to just barely peel back the layers of understanding why mass is a thing. What is mass? Well, like time and space, mass is defined in the context of its measurement. You put the thing on the pan balance. That's how mass is defined. Not necessarily a pan balance either, because that's only one way of determining the mass. There's another way, and you just wiggle something back and forth, and you can determine its mass that way. It's not associated fundamentally necessarily with gravity. This thing. I couldn't help but think just then that sometimes when I talk about, this is hardly related at all, but I'm getting myself accustomed to the fact that this discussion is less formal than when I did it the first time, and so I can be more casual with it. So I get to the point at some point where I demonstrate that with orbital mechanics I can figure out the mass of the sun based on the motion of the planets. That's a measurement of the mass of the sun itself based on the observation of the planets. And then it's very dramatic, and I do the equation, and so that is the mass of the sun based on the orbital mechanics. That's how we know. And I don't know if there's anybody here who witnessed this happen. I was like, so that's how we know. And then I did make the joke, because after you get the physics done and you're happy that you've said it just the right way, then you can make a joke at the end. It's sort of like a little reward that you give yourself. And I said, what did you think? Do you think we took the pan balance and we put it against the sun? Read the numbers off it? No! The sun is far too hot to put a pan balance against it, which is a joke because that's not even how you do that, right? And a young man in the back, bless his heart, what did he say? I wrote up here on a sign. Why don't you just wait till it's nighttime? My point is this. Mass is a fundamental measurement because mass is only defined in the context of its measurement. So for the first semester of our physics, it's space, time, and mass. Those are the fundamental measurements. Those are the fundamental units. Everything else is constructed from them. Everything else is constructed from them. Everything else. And now, Shadi, what about newtons? A newton is a kilogram, mass, meter, space, per second squared, time. Every physical quantity in our classical mechanics is some combination of meters, kilograms, and seconds. It's some combination of space, mass, and time. So therefore, this thing that I've been saying that's like really obvious, and maybe I'm formalizing, no, there's something really deep and special going on here. I don't want to share the deep and specialness with you because it's like the best part of doing this kind of physics. Is that I've been saying kind of like a funny story, and nobody gets the depth, well, you're going to get it in a minute because you're going to think hard about what I'm saying. As I say, I look at the universe and I measure the positions, and then I turn my back and I look again. And you might think that that's just like an instructional story. It's just a thing that I'm saying to sort of convey to you the idea. No, it's deeper than that. It's much deeper than that. Much, much deeper. Let me explain to you why. I look at the universe and I can measure the positions and velocities of everything. Now, velocity is a combination of space and time, meters per second. By the way, velocity is space and time, which is why when Einstein started messing with space and time, that was kind of a big deal. It's a big deal to classical mechanics. If you reimagine the way space and time work, and in particular when you discover that space and time are interrelated, that they are not actually separate from each other, that they're in fact one thing called space-time. But we'll get to that. But so I look at the universe and everything's positions and velocities. And then I turn my back and I look back again and it's all positions and velocities. I need to get the mass in there somehow. And I think many of you know that later on in our course there's going to be a quantity called the momentum. Momentum is the product of the mass and the velocity. And that's okay. If that shouldn't bother you if I say that. But just in case it does, don't worry. We're going to talk about that later on. So I create a new quantity called the momentum that I don't need for this discussion, but for this story that I'm telling you, I do need. So the momentum is equal to the mass times the velocity. So now let me change my story, because now I can include the mass in my story as well. So I look at the universe and I see all of the positions and I see all of the momenta of every particle in the universe. It's pretty epic. By the way, an unknowable thing, right? An unknowable thing. That's too much information. How big would my flash drive have to be to store the position and momentum of every particle in the universe? No, not even. I'm going to add a sidetrack to my sidetrack, Hannah, because you said that. Dang, curse you. I'm going to say really quick. Someone asked me one time, Shiley, what's the biggest number that means anything? Right? Because you know that game that you play with a kid, like, I hate you. I hate you times a billion. I hate you times a billion times a billion times a billion. I hate you times a billion times a billion times a billion plus one. So numbers can get arbitrarily large. And when we do our calculus, what? We got positive infinity and negative infinity. You know, I'm going to go a third level. It's like Inception. I'm going into dream after dream after dream. Here's a third level. I just was reading a math problem, and in the math problem, it said that it had to do with limits and whatnot, because I've been doing calculus in my spare time, because I'm crazy like that. It said can go to arbitrarily large values, arbitrarily large positive values. That's plus infinity, right? Arbitrarily large positive values, that's plus infinity. And also, right, you and I would say, therefore, arbitrarily large negative values at negative infinity, right? That's what we would say. Go to plus infinity, arbitrarily large values of positive numbers, or go to negative infinity, arbitrarily negative numbers. Isn't that great? That's not what it said. It said arbitrarily large positive numbers, positive infinity, and it said arbitrarily negative absolute value of negative infinity. I think the math folks, honestly, I'm suspicious. Just like I'm suspicious about the air conditioning, I think the math folks are deliberately saying things in ways to prevent people from doing math, because math is the only thing they have, and they're desperate to hang on to it. If other people start to figure it out, then they'll be like, no, come and talk to me. No, you math nerd, we understand your game. So, but of course, positive infinity is not a meaningful number. It's a mathematical object that we use to describe numbers that are arbitrarily large. So someone says to me, Shadi, what's the biggest number that means anything? So I give that a little ponder. What's the biggest number that means anything? And so I work that out, right? I could be wrong. Find a number that's bigger than this one, but still means something. So far as we know, electrons are immortal. Once an electron exists, unless it para-annihilates with an antimatter electron, obviously. But an electron of its own accord is sort of immortal if nothing happens to it. But just like nuclei, which can radioactively decay and transmute into other elements, protons can decay, they disintegrate. They have a half-life, which is a thing you probably talked about in biology, about species of carbon. By species, I mean, of course, isotopes of carbon that change, and you use that for carbon dating. Protons have a half-life. They disintegrate into a whole bunch of exotic subatomic particles. So all of the protons, this is alarming, all the protons that currently exist in the universe are dying. They have a half-life. They'll all spontaneously disintegrate. So if you're looking for a statement of when is the end of the universe, I would say that that's when all of the protons have disintegrated. Because when the last proton disintegrates, on the day the last proton disintegrates, it does. That's exactly what I was thinking, right? Or I was thinking my autobiography should have that. The day the last proton disintegrated. As soon as, on the day the last proton disintegrates, there's no such thing as hydrogen. On the day that the last proton disintegrates, chemistry ceases to exist. Physics still exists, but chemistry ceases to exist. I think I've just proven that physics is a more fundamental science. On the day the last proton disintegrates, there's no more hydrogen atoms. I'm calling that day the end of the universe. I'm calling that day the end of the universe. And that day is going to happen a certain number of seconds from now. And that number of seconds, according to me, is the largest number that means anything. Because after the last proton disintegrates, you don't have to go home, but you can't stay here. The universe is closing up shop. Nothing more to see here. Move along. And also nobody there to see it. So that is 10 raised to the 10 raised to the 76 seconds. That is the biggest number, so far as I can tell, that means anything. No, your calculator will barf on that. Half-life of proton disintegration. Based on the current mass of the universe, estimating the number of protons available, calculate that half-life for all the protons to disintegrate to zero over that time. Involves a little integration as it asymptotically approaches zero. Cut off the number. Then, of course, that's an estimate. You're not going to be there going, Charlie, you said. Yeah, my watch is disintegrating, but it still says you're wrong.
So would you say that we have a significant amount of...
I would say, yeah, I can say you can take the day off. That's not what I meant. I meant take the rest of the day off. This class, obviously, this is the most important thing you'll do today. So this class, and then after today, feel free to take the rest of the day off. Feel free to tell them that I said so, and feel free to then immediately realize that nobody gives a damn about my authority and such things. So you'll find out. So I look at the universe. See how I brought it back? I was 3 deep, man, and I brought it all the way back. I look at the universe, positions and momentum of every particle in the universe. That's a lot of information, but let's imagine that I know it. We call that the state. Oh, it's getting exciting now. The physics is zhuzhy. The state of any physical system, including the universe at large, if I want to get gutsy like that, is described by the set of all of its position and momenta of all the particles that make it up. It's called the state. All of the positions and momenta. And the positions and momenta evolve in time. And so I need an equation that describes how the positions and momenta evolve in time, by the way. And so I'm going to write that equation. Now I'm getting silly. I'm just going to get silly for a second, all right? There's the equation that governs the evolution of the state of the state of any physical system, and that is all of classical physics in one statement. Well, a couple of statements there, a little Georgie package. The state of the system described by all of its position and momenta, and then Newton's second law. Charlie, what the hell? That's not Newton's second law is F equals ma. I've just written there the sexy big kids version of Newton's second law. The negative, the gradient of the potential is equal to the partial derivative of the momentum with respect to time. That's F equals ma. See, just like the math folks, I can make things deliberately complicated to look at. So the state of the system is described by all of its position and momenta, and our physical law, that is Newton's second law that governs classical mechanics, describes the evolution of the state of the system. Yes! Now, I got a little grandiose to the universe. My system can be support with a string that hangs and a mass on it and it swings back and forth. That could be the system that I'm describing. And it has a position and momenta at every instant in time, and I find a way to describe the position evolve as a function of time as the position and momentum change in time continuously. Here's the problem. The state of the system is described by the position and the momentum, and the position and the momentum change continuously in time. That is called a trajectory. A trajectory. Here's the problem. Here is my marker. It has a position in space. There it is. I'm not being crazy here. I'm actually describing the limitations of our science. I look at the marker, there's its position. I've made a measurement of position, X. When I look at it, oh, okay, I thought you were like looking at the marker. I thought you were trying too hard. You were doing like a thing like, it's not like there, parallax. There's the marker, it's position. The casual reality of this is I'm making continuous measurements of position. I look at it, continuously measuring its position. There it is. That's not the reality of the limitations of our measurement. Our measurement is actually, I make one position measurement, that's the location. I make a position measurement, there it is. Now I turn my back. Now the only information I have about the position of the marker is the position that I just measured. One number describing its position. Jeff, would you move the marker, please? Now I turn back again. And now the marker is in a different position, and I make a new position measurement. From that, 2 measurements of position, I get a displacement. And from the displacement, I can calculate a velocity on average and an acceleration on average. Do I know what the marker was doing between measurements? No, I do not know. The fact is, I do not know. And your little primate mind goes, yeah, Charlie, but you know what happened. Jeff took marker and he just scooted over. You know. No, it's not scientific. The science is I made a measurement and I did not look. We moved. And now there it is. Well, Charlie, you got to look. Go ahead and look. No. Because imagine I'm describing the behavior of electrons and the electron's going there. Now you can't see an electron. You can't see an electron going along through here. So I make a measurement of an electron. Charlie, how do you measure electrons? Well, that turns out to be quite tricky, measuring electrons. But let's say I have an electronometer meter, and the electron goes by. There it is! Write that down, the position of the thing. Now, the electron's moved on, but you can't see it. The existence of the electron is defined in the context of its measurement. So then you come over here and you measure it again. There it is! You don't know what it was doing in between. Is it possible that instead of going straight from one to the other, that it went along a bit, winked out of existence, appeared on the other side of the universe, winked back again, traveled, did a little loop-de-loop just for fun, and then arrived at the other position? Right. there's an unknown aspect to it. There's an uncertainty to it. The limitation of human observation. You go, but Charlie, but that's just look more often. Take your examometer and go along with it and measure the position. You cannot! It turns out to be a fundamental limitation of human observation of the universe, a fundamental limitation that you cannot know the position at every instant in time to arbitrary precision. Cannot. Have we heard of the Heisenberg uncertainty principle, which is an aspect of quantum mechanics? The Heisenberg uncertainty principle describes this fundamental limitation of human observation, which I just haven't made a good enough microscope yet. No, it's a fundamental limitation to this idea. So in classical mechanics, we have an idea of the state of a system being described as a continuum of positions and a continuum of momenta that we call a trajectory. And it turns out that idea is false. It turns out ultimately that when we start to describe things on the very, very small scale, microscopic things, like I didn't have trouble with the marker, but you see I immediately have trouble with the electron, that we need a new kind of mechanics. Not a continuum mechanic, but a quantum mechanic. And it makes me so very happy. So under this position, velocity, and acceleration, there is something much sexier going on, something that's a lot of fun to deal with, and that we'll get into talking about. I never remember how much time that I have. But it's not, see, sometimes I get burned by special event schedules. I was on a tear yesterday at 2:15 when all of a sudden we were like, let's go home. And everybody was like, Charlie, it's cool and all, but I'd really rather be at home right now. Let me do a little bit of work with these two quantities. The displacement is easy. I simply subtract the final position minus the initial position displacement. It's fine. Let me work with these two quantities, the velocity and the acceleration. I can do a little bit of algebra to it, and I'm going to make a realization here with my delta t. Delta t is the final time minus the initial time, and just like the initial position, the initial time is arbitrarily chosen. I choose when I start my stopwatch. So delta t is an interval of time that passes. I'm going to very casually and recklessly, in a very non-mathematical sort of way, and an imprecise sort of way, say I'm perfectly comfortable with saying, instead of delta t, let me just write t. And I'll say delta x divided by t, because there I'm making an assumption that the initial t is equal to 0. So please forgive me that notation, but I think it's cool. I think it's cool. So what does this equation tell me? Well, I know that the displacement, I'm just going to do a little bit of algebra with it here. I know that the displacement is the final position minus the initial position divided by this interval in time. That's great. A little bit more algebra. And I'm going to express this equation as the final position is equal to the initial position plus the velocity. The velocity times time. The position at some time in the future is equal to whatever the position is now, plus the average rate at which the position changes multiplied by the time. Remember, this is meters per second. So if I take meters per second and multiply by seconds, it's a certain number of meters that when added or subtracted to, because that could be a negative quantity, that when added or subtracted to the initial position gives the final position. Since the velocity is defined only on average, when I write this expression, I must appreciate that that number might have changed during the interval. It might be lesser, it might be greater, it might be crazy. Which means my prediction of the position in the future is only determined on an on-average sort of way. It's only an approximation. Now, we get a little bit more demanding like that. Charlie, I want to know exactly what is the position in the future. I'm going to give you some initial conditions, and I give you a time. I want you to tell me, where is it now? Exactly. By the way, as a practical matter, that's impossible. As a practical matter, that's impossible, because there are all kinds of factors influencing the experimental result of the thing. But we'd like to at least theoretically predict an exact result of the outcome of that. Here is the problem that I've just described again graphically. I'd like to calculate the position at some time in the future. So here's what I'm doing. Imagine I make a graph. It's going to have to be bigger than that. I apologize. It's going to have to be bigger than that for it to have all of the stuff that I want. Imagine I make a graph of position as a function of time. In order to apply this equation, I'm going to have an initial time, t0. That's okay, I can have an initial. And I'm going to have a final time. Here's the initial time, t0. Here's the final time, t. You understand a little bit? I regret that I said just make it t, but it's all right. We understand what I'm talking about. I'm going to have an initial position and a final position. So I have an initial position, x naught, and a final position, x. So this is my graph. This is the information that I have. So I have an initial position, x naught, which is at t is equal to 0. And I have a final position, x, which happens at t. And there are those positions. There are those positions. The trouble is, that is my data, and my data is very, very sparse compared to the reality. Now imagine that I have godlike powers. I have godlike powers, and I can determine exactly what the motion, which is very godlike indeed, that I can know the position at every instant in time above our physics. And I can show you the truth of this. And the truth of this is that it looks like this. That's the position at every instant in time. Now, when I calculate the average velocity, the way that I hate it, it's so ugly. I drew it, it was ugly, and I didn't react because I didn't want to be like, ah! Pardon me. There are my positions. By the way, the last time we went through this, I would have stopped the recording and started again. This time, you screwed up, Charlie. I know. It's terrible. It's terrible. Terrible, terrible, terrible. If I want to calculate the average velocity in this situation, obviously what I'm going to do is follow the prescription according to the definition of average velocity, which would be the change in position over the change in time. What that's going to be, I think we all know, is going to be the rise and the run of this graph, because the change in position is x minus x naught, which is this along the x-axis. And the change in time is t minus t naught, which is along the time axis like this. And so what I get for my average velocity is effectively, since it's delta x over delta t, it's the rise of this graph divided by the run of this graph, is the slope from this point to this point. Try to draw a slope through two lines that you've already drawn. Whew! I did it! It's tricky to do. Give it a try sometime. Tricky to do. This line, the slope of this line, is the average velocity. Which, see, the average velocity is not giving me the full description. It's not giving me what I want. I want to know what is the velocity at every instant in time. I don't want to know what is the velocity on average, because the average velocity is wrong in terms of the description. Because look, here early on in the interval, you can see that the slope of the actual trajectory, which I have godlike powers to know, that the slope of the actual trajectory is quite high. That is, the particle early in the interval, it turns out, is going very fast. And then as time goes on, the slope becomes shallower and shallower, and actually shallower than the velocity on average. And so at the end of the interval, it's going quite slower. And so I'm missing out on the description of the true description of the motion of the thing, the true nature of the thing. I'm missing out because my average velocity doesn't give me sufficient information. And you might look at that and you say, wait a second, Shadley, I'm curious. Things could have worked out better for you if you hadn't have made the interval so, because it's just like this. If the marker's here and I turn my back and I'm talking to the wall and there's Jeff doing a thing, moving the marker around, and I turn back again, the marker's in a different location. You say, Shadley should have watched the whole time. That is, I should be watching continuously. Now, your vision doesn't work continuously. You know that, right? Light goes into your eye. Your brain forms image after image after image at about 16 images per second. That's what the human brain can do. That's why we run film at 32 frames per second, double that, so your brain will get the impression of continuous motion. Film is not continuous motion. It's just a sequence of images shown in rapid succession. 32 frames per second, and seems like 64 what now? Yeah, now they put the 64 and more frames. More and more frames, it's so real! Right? It's more real. Raise the frame rate up, get more and more frames per second. By the way, if you think about it, it's the reason why if you're sitting in the parking lot watching cars come and go and whatnot, a car speeds up. The hubcap of the car appears to go forward and then appears to go backward and then appears to go forward again. Have you ever noticed that? Yeah. That's because of the frame rate of your eye. Right? It's speeding up, and the tire rotation has a frequency of rotation, and that's what's causing that optical effect. Of course, the tire's rotating forward the whole time. So human observation is flawed, but you say, no, it would be better if you actually looked closer at it. Because the reality of this, and here I am actually looking closer at it, the reality of it is any curve that you have, any curve that you draw on a graph, and you can probably do this on your calculator, graph something funky, and then zoom in on it, and zoom in, 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 and zoom in. Every function you zoom in close enough looks like a straight line. And if I find the slope of a straight line, then that slope is exact. Because the slope of a line is y equals mx plus b, and that's exact for a line. Not for some curve like this. No, that's not y equals mx plus b. It's something strange. Maybe it's I don't know what it is. But it's not y equals mx plus b. But if I zoom in close enough, you say, watch it more closely, Shadley. Instead of, you see this big interval here, t minus t naught is huge. Don't do that. Look much more closely. Look at a much, much smaller interval, right? Well, if I look at a much, much smaller interval in t, then that means I'm going to be looking at a much, much smaller interval in x. Much, much smaller. The interval is very wee, both in time and space. It's very wee. Very, very small. If I zoom in there, then right here on my graph, I'm going to get a slope that is practically constant. It's very nearly constant. And that will give me the slope at that point. And that can be the velocity, not on average at that point, but exactly at that point. You say, Shadley, no, it's still a little bit curvy. What are you doing? Okay, I'll make it even smaller, all right? Yeah, still curvy, Shadi. Okay, fine, I'll make it even smaller. You know what I'm going to say. Still curvy. But an important observation here is I can make the interval arbitrarily small. There's no limit to the smallness of it. If you don't like its smallness, I'll divide it by 1 billion. If you don't like that, I'll divide it by 1 billion. 1 billion plus 1, right? The same childish argument. That is, I can take the interval, this tiny little interval here, and I can make it arbitrarily small so that it's not delta t, d is in delta, delta t. It's not delta t, it's dt. I've just replaced delta with d. I've just replaced delta with d. And on the x-axis, instead of making it delta x, I'll make it dx. That is, over here, I'm going to define my velocity not on average, but instantaneously by making the interval arbitrarily small. And that's why I use a different notation, the differential. But don't be fooled. Delta x over delta t is exactly the same thing as dx over dt. It's exactly the same thing. See, it's notation causing you to think, oh no, this is different, it's scary, I don't want to get... It's exactly the same thing. And you can treat it the same thing, same way. It's just instead of delta being a big chunky delta where I turn my back and I'm not watching, I look back again, now the delta is infinitesimally small. It's arbitrarily small. And when it's arbitrarily small, the value that I get for the velocity becomes not a velocity on average, not a prediction on average, but a prediction exact.